Yes, so it's about improved unit inference and checking in Modelica, and it will mostly be just generic how this is done, but all of the things I will present are implemented in Daimler 2026X, which will release now, and almost everything was in the previous release, and it's also on the pre-experience platform. So what I will go through is first a little background on units, and then how the simple unit inference and checking works, and then go to Hindley-Milner, and then do a theoretical comparison between them, and also do it practically for some libraries, and then indicate some future work. So the basic question here is, why do we have units? And the first is that it gives better models, because you can detect if you add a length to a mass. That doesn't make sense. And that's the dimensional analysis, and that's long history of physics. And then if you can still have arrows where you mix different units that are sort of compatible. So, and then you can use empirical units instead of SI units, and lose a Mars rover, climate rover for $327 million. So it can be costly to mix up units. However, having correct units is necessary, but not sufficient. And it also gives a better understanding models. You say 2 million Pascal, not just 2 million. And you can say 20 bars with and 20 degrees Celsius, or slightly more in this room, instead of in Kelvin. And unit inference is that you get units for variables without declared unit. And that's sort of a by-effect of actually checking the units for everything. And then there is one thing that the SI standard says is that even if units are compatible, you shouldn't mix them. So energy is in joule, whereas torque is in newton meters. They are formally the same, but don't mix them. And similarly, hertz is for frequency, whereas angular frequency is radians per second, and radioactive things are in becquerel. They're all the same, but you shouldn't mix them. And so what we have in Modelica language, we have a unit attribute, which should be in the base units, and mostly is. And then we have a display unit for displaying and inputting things, which can be in any other unit. And the benefit with the design is that you don't have to know the display unit. The models still work, and assuming you have a base unit in the unit. And then you have arrays in Modelica, and there we have one complication is that the array elements can have different units. So if you have a state space controller or a filter, then it's quite normal that you have different units for the different elements. That's something to consider. And then we have quantity attribute and absolute value. I will not go into them. And what you do is based on the SI standard, but radians is almost treated as a base unit. And that's also seen in the FMI standard, where we have the 7 base units and radians. And then we have a proposed but not decided unit checking from Francesco Cancella, so that you can write capacitance C equals 2, and the 2 has the correct unit. If you say energy is T times V squared divided by 2, the two 2's here have implicitly the unit are dimensionless, so we have unit 1, and then it works. And you can't get the unit, this 4 here. It could be 4 volts, and then it would work, but we don't. That's disallowed by this proposed unit checking, because you don't want those mistakes. So then we go to the simple unit checking, and it was introduced by Sven-Erik Mattsson and Henning Elmqvist and implemented in Daimler quite some time ago. And what you first have in traditional programming languages is that you can do very simple unit handling by propagating units sort of upwards. So if you have 2 terms with a unit, then if you add them, the sum is the same unit. And if you multiply, it's the multiplication of units. That's quite common in libraries in many languages. What we add in Modelica is that you have equations, so you have to propagate it from either side, sort of sideways, and also down to the terms. So here, if you have a torque with unit newton meters, then and connect the sine source to it, then the sine source get the same unit, and the offset and the amplitude also get the unit, assuming that you know that the sine function output has unit 1. And the full algorithm for this is you just do this for all equations and expressions a handful of times, and based on the previous ones, and it's normally enough with a handful of times, and you have 2 rules for all operators, one for going up and one for going down. And then the original rules were literals, were wildcards, except for 1 over x, where 1 was assumed to have unit 1. Now, as proposed in multiplication and division, we have those stricter rules. And the advantages with this simple unit checking is that results are traceable and it's easy to understand. If you get the unit for something, you can see that those operands to it had units, and then I can trace that back. It's nothing strange. It's very local, everything. And it preserves units. So you don't, even if you have base units, you don't, or even if you have 7 base units in the SI system, you don't have to convert to them. You can just use Newton meter and get that. And for arrays, there's another advantage, is that everything here works even for homogeneous arrays. So if you have an array where all elements have the same unit, and you add it with another array that has the same unit everywhere, the result also have the same unit, and it's the obvious same unit. So you don't have to do anything special for arrays for this. However, what is done specially for arrays is that you can propagate it one-sided. So if one of those 2 sides, you can propagate from A, and when taking the element to every element you take off it, FA has a unit because it's homogeneous, so all elements have it. And similarly, if C has a unit and you concatenate A and B to give C, then both A and B must have a unit. Or if A and B have a unit and it's the same unit, you get the same unit for C. But you don't. But you still allow all the mixes, even though you have this possibility. So that's a good part. The bad part of this simple algorithm is that it's an ad hoc iteration. You sort of iterate until it's done, and you duplicate the rules because you have one set of rules for going up and another set for going down, and it's a bit a mess to do. And then it's not clear if it finds everything, and it depends slightly on how the equations are formulated. Not only with the literals, but also without literals, it will depend. We will see one example of that. And then we have a Hindley-Milner. And before looking at this, I used to think that it was Hindley-Milner that invented this unit checking, and that it's more complicated than the simple one, there's the name. And it can handle everything the simple can, and it's a lot better, or possibly it's the same as a simple one. However, that's not none of that is really true. And now we will see what it actually is. It was Andrew Kennedy. I don't know if it's related to any other Kennedy who invented it. And the basic idea is that you collect the unit equations from expressions. You just collect all of them, and then you use a variant of the Hindley-Milner or Damas Hindley-Milner type inference to infer units for that. And when you get a unit equation, so you have a unit of one or more variables and some literal units in multiplied and divided by each other. And if there's just one variable which says unknown, if there are 0 variables in it, it should be a literal unit that is dimensionless, otherwise there's an error. And if it's an error, you should report it. If there's one variable that has unknown unit, then you get that from the equation. The new thing is that if there is one variable, whereas more than one variable, you can solve for one variable in terms of the units of the others and the literals. So you get a substitution there. And then you repeat this, not repeat, you go through all those unit equations in order. And when you get the result, you substitute in the other equations and in the other substitutions. And when you're going through all the equations, you have the result. So there's no iteration or anything. It's just going through everything. So it's sort of linear, and it's a solid foundation for it. And some of you may know that you can get, in physics, you have unit equations that you solve, and you solve that by solving an integral linear system of equations. And it's basically the same. The integral linear system is the logarithm of these equations. And it finds slightly more than the simple one. So here is an example showing the benefit. And here are the two substitutions based on the units for k and y, which are declared. And then you get this unit equations. The unit of k times the unit of u is equal to the unit of u. And you solve it by substitution and give it the unit of u is also 1. Then from yd equals there y, you get this equation, and you solve it to get that the yd is seconds minus 1. And u alpha 1, which is an intermediate variable to be able to talk about it, is unit of the omega times unit of u. And you see that the unit of alpha 1 is then unit of omega. And then you get two additional unit equations. Unit of alpha 1 is, let's see, unit of alpha 1 is this one, which is a unit of omega times the unit of the multiplication. And the multiplication has the same unit of y. So you get this one. And then you have unit, you have a here you have a this one is alpha 1, and this one is unit of d times unit of yd. So that one gives a second to last equation. And then there of yd is omega times alpha 1, etc. So that gives the last equation. And you see all of these I have solved to give some ones. And these two are the remaining ones that are interesting. And the new thing here is that based on these substitution and everything, I get a new equation here that I couldn't get for the simple algorithm. That is, the second minus 2 is equal to unit of omega 2. Now, I don't solve that one immediately. I go through them in order. So I solve for unit of omega in unit of omega is unit of d times s minus 1, which substitutes that unit of omega is unit of d time divided by seconds. And then I substitute it in the equations for unit of omega, well, the last one, and then I get that 1 equals the unit of d squared. And then I solve that for the unit of d, which is 1, and then I said get the unit of omega is per second. However, that is something the simple algorithm couldn't do. If you had formulated it slightly differently with omega squared times y to factor out this, then you could have solved it. But the Hindley-Milner gives this same result even without that, and even if you didn't have a unit for y. However, note that it should be SI angular frequency omega, not SI frequency omega. And the disadvantage with this Hindley-Milner is that it infers too much for arrays. So if you have t times their x equals to a times x, it will infer that the unit for a is 1. However, if this is an array equation and x has is an array with meters and seconds, then a is a matrix with weird units, but that's something that can happen. And the possible solutions of that we will use is to just skip the arrays. It might be possible to do something else, but it's very complicated to scalarize while keeping the unit information. And the advanced thing, I don't know exactly what it would be. So if we look at it in practice and run it for MSL, we see that there are about 300,000 scalars. Well, they're counting multiple times, and 200,000 of them have declared unit. And the simple inference gives 9,000 additional scalars a unit. And the Hindley-Milner just gives 44 additional units. And they are of 4 different kinds. This is one where you have a squared, an r times r, that you figure out the unit from the square of it. And then there's something with noise min, and then there's previous second order example, and one additional second order, which is done electrically. And you don't get any new errors. And you see that all the And if you take a slightly smaller example, a famous fluid stream, it's similar, but slightly smaller. So that's very smaller numbers. And here, the Hindley-Milner didn't give anything new. So let's go through this second order the electrical example. Here you have typical electrical thing with some numbers everywhere. And with this proposed thing, you would get that the unit, and just applying the rules, you would get that the unit of D is per ohm, and unit for omega is per second. However, if you look closely here, you see that there is an 00004, and you have 250 everywhere. And if you think a bit more, that's 1 over 250 is 4,000. So if you introduce a common parameter for all those 250 and call it R, you see that it's the unit of R that is ohm. And unit of D is 1, and unit of omega is per second, exactly as in the previous second order example. So you have to be a bit careful with doing units, and don't write real omega time constant of motor. Write that it is an angular frequency. It's much better, and it would be good if Modelica standard library has something for declaring unit with unit 1 as well, for damping constants. So now we can get to see the combined algorithms to get the best of the two worlds, because the simple algorithm can be seen as sort of running the Hindley-Milner first draft of it. But you don't simplify, and you only solve the trivial equations, and you have to introduce intermediate unit variables in order to keep it possible. So if you do that, and you can run this for all equations and also handle the one-sided array equations, and then you continue with the scalar unit equations from the previous step and run the full Hindley-Milner on that. So the future work now is, for tools to implement this combined algorithm. For the Modelica language specification is to get agreement on these proposed rules and add an escape mechanism for various things, including possibility to do unit conversions and declare that you are doing unit conversions in the model. And for the libraries and user models, the first thing is enable unit check and fix the unit errors in your models. And the second, slightly more advanced thing is use square root and the newly introduced nth root instead of raising x to the power of 0.5 or x to the power of 1/3. Because then we can do unit inference for that and unit checking. We can sort of do it, but you don't know that it's really the correct way. And for the future, it might be possible to see if we can do more advanced unit inference for arrays. That's one possibility. And I don't think it will be significant, but it will be good. And also a possibility to do modular unit check. And now the conclusions. Oh, well, I'm ahead of time. It does detect, unit checking does detect errors and makes it better, have better models. And this paper should give a better understanding of how to do unit checking and inference. But still, it's even if you have unit inference, it's good to declare things with unit instead of having this problem with omega, etc. And the Hindley-Milner algorithm is easy to implement and can infer a few additional units for scalars. And it's more interesting is that the combined algorithm is also straightforward to implement, and well, together with Hindley-Milner, and gives advantages of both of them. Yes, so that's all.
Yeah, thank you very much, Hans.